point.
I've got my first interest in it back when Halley's Comet passed last time. And yeah, it was cool. I don't know if I'll still be alive to see it again, but I started noting, and that was whenever I first started looking. I wasn't even, this was before I was in undergraduate school, right. So it was like I would, but I did get some interest in it at that point, and looking into things like the phases of. I got a little telescope and reflecting telescope, but then I could see the phases of Venus, and and I started seeing like the rings of Saturn, and like, oh wow, this is so much different than seeing a picture in a book. Uh-huh. You're talking about Jupiter, right? Yeah. This is this was like the seminal moment for me and it was when I had started undergraduate school, and I was on my way to campus one morning, and this was my habit. I would leave before sunup and get there so I could get the good parking spot, sit down and drink my coffee and relax and get ready for the day in peace, and not trying to hit the ground running and be rushed when I get there. So I'm driving to work or to campus in the wee hours before sunup, and I noticed Jupiter, and the sky was so clear that I realized I could see 4 of Jupiter's moons with my naked eye driving on the interstate that morning. Oh, it was just, it was a tremendously clear, dry, no humidity, wee hours of them just before sunrise, but it's still pitch black, and it was like, there they were. Like I realized, that's Jupiter, and that's actually her moon. Those are 4 of the moons. Like, wow. Yeah. So, what questions do you have from the homework, or do you have any questions from the exam?
I do have a question. I wanted to make sure that I was doing the OGAD graph properly. I don't think I did on this part.
Yeah.
I'm still a little confused on what needs to be X and what needs to be Y.
Let me see what you did here.
And I might have to decipher before because I have chicken scratch handwriting.
You can't turn this far? You're supposed to be able to. There you go. You can turn this far. Whoop, not that far. Back up. Come back. There you go. You can do it. I knew you could. Okay. Let's just do an ogive.
Okay.
From one of the examples in the back in last chapter, or maybe on one of the homework examples. Do you have a homework example there where we did one? No, there was one. Is it in 2-2?
There's one at 2-2, and it's number, you could do 3 or 11. There's another one in 2-2 that's number 19.
Actually, you did number 11 when it was supposed to be 13, and I gave you credit for it anyway.
Oh, did I? My bad.
That's okay. These things happen. That might have been it. Okay, well, let's look at, you said number 11, right?
Yes.
Okay, well, we have frequency distribution, blood glucose levels in milligrams per deciliter for 50 patients at a medical facility. Construct a histogram, frequency, polygon, and ogive for the data. Okay. Well, let's start with our class limits. This is number 11 on page 67, so I'm going to get you to call out the numbers to me. What are the class limits? Okay. So they're 5 each, right?
Yes.
5 wide. And the boundaries then will be, and this was something that I noticed everybody watching this video should probably pay attention to, because this got to be a little confusing for some of you. The boundaries here would be, these are all 2 digits. So the next digit would be the first decimal point. So you go to the first decimal point and subtract 5. That brings the lower boundary to 59.5. And the upper boundary would be the next, add the decimal point and go up 5. So it would be 64.5. You add 5 to the next digit, okay, to establish the boundaries. Now that means this one would be the same boundary as the first one. 65 would be 64.5 to 69.5, 69.5 to 74.5, 74. Read these class limits to me again. What's this one? That should be 75, not 73, right? Okay, 74.5 to 79.5, 79, he said, as he wrote 97. Seven. 79.5 to 84.5, 84.5 to 89.5, 89.5 to 94.5, 94.5 to 99.5. So, those are our boundaries. Now, call out the frequencies for me. We don't have to do tallies. We're not tabulating the data ourselves. Let's just call out the frequencies for me.
2, 1, 5, 12, 18, 6, 5, 1.
Okay. Now, we are going to produce a histogram, a frequency polygon, and an ogive. So we're going to need the midpoints of these also, and the relative frequencies. What's the midpoint of this one? 60 to 62. Okay, so now we can find the midpoint by taking the average of these two, of the class limits. 60 plus 64 is 124, divided by 2 is 62. So let's write midpoint. We could not find the class width by subtracting these. That would give us 64 minus 60 would be 4, but that's not the class width. The class width would either be, it could be this minus this, 64.5 minus 59.5, which would be 5, or you could take this limit and subtract that limit. Not limit, yeah, this class limit and subtract that, the adjacent class limit, and that will give you the class width. But not this minus that, not the limit minus the upper minus lower limit. So let's go ahead and write our width just for good measure. They're all going to be 5, because if they're not, that was something else I wanted to point out to you on one of the homework problems. I don't remember if it was you or if it was one of the other students, but somebody was asked what was wrong with these with these tabulations, and there were 2 of them. In both cases, one of the principal problems was that the classes were not uniform width. There were some that were different widths. But in the case of the second one, there was a second problem in that the class boundaries overlapped, which cannot happen. If 64 is a boundary for, not a boundary, but a limit for this class, it cannot be a limit for that class. 64.5 can be a boundary for both, because it's a boundary, it's between the class limits. Okay, and it just shows us that if there was something that fell between those class limits, it's already been rounded so that it goes into one or the other. But anyway, now our midpoint for the next one, 67. And we add 5 to 67 and we get 72. And add 5 and get 77. And add 5 and get 82. And add 5 and get 87. And add 5 and get 92. And add 5 and get 97. You notice how once you find the first midpoint, you can just add the class width and get the next midpoint. And of course, they're all still 5 wide. Now, what is our total? 50, right? Let's see. 18, 20, 30, 40. Is that right? 18 and 12 is 20 plus 3 is 30. Plus 2 5s is 40. 7, 8, 9, 10 is 50. So that's right. We get 50 total. And look at me doing arithmetic and on the fly, huh? So that means we now have relative frequency. What is 2 divided by 50? Say again, 0.5? No, it's 0.05, isn't it? Oh, okay. That's even better. And what's 1 divided by 50? And 5 divided by 50? 12 divided by 50. $18 divided by 50. 6 divided by 50. 5 divided by 50 is still 0.1. and 1 is still 0.02. That is our relative frequencies. Now let's look at our cumulative frequencies. The first one is still 0.04. What do you get when you add 0.02 to it? And add 0.1 to that, and add 24 to that, you get, is that right? Confirm that for me. 0.16 plus 0.24 is 0.3 or 0.4? 0.4. 0.4 plus 0.36 is 0.76. Plus 0.12 would be 0.88. Plus 0.1 would be 0.98. Plus 0.02 would be 1.00. That is our cumulative frequencies. Now, first we need a histogram. Well, how many classes do we have? 1, 2, 3, 4, 5, 6, 7, 8 of them. So, 1, 2, 3, 4, 5, 6, 7, 8. Is that right? Okay, what's our boundaries? 59.5 and 64.5. And call them out to me. 69.5. Okay, our midpoints are okay. Now, what is our data range? They go from a minimum of 1 to a maximum of 18. Oh, let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And now let's do a histogram. You know what, I'm going to use purple. For the first class, we get a frequency of 2. For the second class, we get a frequency of 1. What's the next one? 5. Okay, the next one.
12.
Okay, the next one is 18, right? Or I'm going around the midpoint of 82. Next one is 6. And then 5. And then finally, 1. That's our histogram. Now, the next thing we're supposed to draw is a frequency polygon. So, for this one, I'll switch to orange, and we'll go right here at the midpoint, 2. This midpoint we'll do 1. At this midpoint we'll do, what was that, 5 or 6? Okay. Point is, we go to each one of these midpoints and we put our data point. And now our polygon, we just draw a line point to point. Boom. So far, this is all right. Now we're going to do the ogive. But for this, I'm going to add an extra axis, a secondary y-axis for the ogive. And it's going to go from 0 to 10, 20, 30, 40, 50, and I'm running out of space, so we'll call this 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100%. Actually, instead of doing percents, I'm going to do it like I would do it. And put it in terms of relative frequency. Now, looking at our class boundaries, how much of our cumulative frequency is below 0%? How much of our relative frequency is below 59.5%? I'm sorry, 59.5 class boundary. Nothing. We have 0 of our cumulative of our data is below 59.5. And this is the important thing when you're doing the ogive. Use the class boundaries. Because we're no longer talking about how much are there. We're saying 0.04 is less than 64.5. Okay, so that's going to be, here's 0.05, so it's going to be about right here at about 0.04. Now, when we get to 69.5, we're up to 0.06. And that's going to be a little above the half. Right there. Now, when we get to 74.5, we're up to 0.16. So that's going to be about right here. Halfway, a little over halfway between 0.1 and 0.2. We get to 79.5, we're up to 0.4. Wow. It's about here. We get to 84.5 and we're up to 0.76. So that's going to be about right here. And then when we get to 89.5, we're all the way up to 0.88. And at 94.5, we're up to 98. And all the way up to 1 at 99.5. In other words, at 99.5, all of our data is below that point. Now, just connect those dots. And that is your ogive. Now, let's use this same data set as we start talking about measures of central tendency. Because this is we are now going to start getting to talking about data that will actually allow you to quantify a description of a distribution, of how this data is distributed. Okay? We're going to talk about measures of central tendency. The first thing I need you to tuck away in your mind and remember this, because it does matter. And this is central to the whole purpose of learning this material. And that is the difference, it has to do with the difference between a population and a sample. If we talk about a parameter that describes a sample, then that is a statistic. Okay? But if we talk about that same characteristic or measure of description that applies to the population as a whole, it's no longer a statistic, that's a parameter. Why do we make this distinction? This ties back to the homework from last time. This is the difference between a sampling error and a non-sampling error. We talk about the population as a whole. Well, what is the mean of the population? The mean is the mean of the population. There's no need to estimate it. If you know the value of everything in the population and you can calculate the mean, that's it. That is the parameter. And that is the goal that you are hoping to approximate as closely as you possibly can from the statistics of that population. But the statistics are those same parameters when they're calculated for a subset or a sample of the population. Okay? This is important to remember. The parameter is the measure or quantity or description. It's the measure of the whole population. When you calculate it for a sample of the population, it's no longer a parameter, it's a statistic. Lost my train of thought. Well, I hate it when that happens. There was another point that I wanted to make, and now I can't remember what it was. Oh yes, back to the homework. There is the fact of the matter is, we don't know what a standard deviation is yet. We're going to learn next time. That will be one of the next measures of variation. Today we're talking about measures of central tendency. A measure of central tendency is the mean. Okay? We can talk about the mean of the population. That's a parameter. When we measure the mean of a sample, we are trying to estimate or predict the mean of the population. But whereas the parameter is exact, because it's the value based on everybody and everything in the population, there's no need to estimate it. The statistic, the mean of a sample, is never ever going to be exactly equal to the parameter, the mean of the population. It's just going to be a best guess. Okay? The reason, the difference between that statistic and the parameter is called the sampling error. Now, despite how that sounds, we talked about this in the previous chapters. That may sound like, well, somebody messed up when they selected the sample. That is not a sampling error. That would be a non-sampling error. That would be a statistician error or a researcher's error. No, a sampling error is simply an expression of the fact that the sample statistic is never going to equal the population parameter. It's going to be different. That's just, you can't help it. That error is introduced because you're looking at just a sample, not the whole population. That is your sampling error. But from that sample, we can still take into account, quantitatively take into account, that this sample is going to has some uncertainty in it, but we can still quantify that uncertainty and make predictions about the parameter with a quantifiable measure of confidence or certainty. Or stated differently, with a quantifiable, calculable measure of uncertainty. Now, the first the measure of central tendency that we're going to talk about is the mean. And that's just the arithmetic average. That's all it is. It's sometimes referred to as the arithmetic mean. Okay. It's denoted in statistics as X bar, the arithmetic mean, or arithmetic average, the mean, and it's equal to the sum over n. Well, you know what? Let me rewrite this. The sum over I equals 1 to n of x sub I divided by, don't want to divide that yet, all divided by n. Okay, you know how to do an arithmetic average. You got 12 quantities, you add them up, divide by 12, and that's the average. Yeah, they give the example here. The mean of 3, 2, 6, 5, and 4 is 3 plus 2 plus 6 plus 5 plus 4 equals 20, divided by 5 equals 4. So the average of those 5 values is 4. Okay? But remember what I said. There are three lies, three kinds of lies. Little lies, big lies, and statistics. So, and again, this is part of the whole purpose of learning this, is so you can figure out how to do this honestly, and how to recognize when someone else is using it dishonestly. In other words, don't let someone tell you that if they put one of your feet in a bucket of boiling water and the other foot in a bucket of ice water, that on average you're going to be comfortable. It's not going to work that way. The mean is probably one of the most common. It's in fact is probably the first statistic or parameter that you're ever going to hear talked about. But it is not the only measure of central tendency. There's also the median. This is the mean. The next one is the median. What is the median? It's just the midpoint of the data array. The symbol for median is uppercase M, uppercase D. Find the median. You arrange the data in ascending order. In this case, what's our data? 1, 1. We got 1, 1, 2, 5, 5, 6, 12, and 18. 1, 2, 3, 4, 5, 6, 7, 8. We got 8 of them. What's the median? Well, if we had 9, if we had an odd number, say we had another one that was 20, well, then the median would be 6, because that's the one right in the middle. Wait, is it? No. Would be 5. Because we've got 4 above it and 4 below it. It's right in the middle. Has nothing to do with the value. It's the midpoint of the data in ascending order. But in this case, we don't have a nice odd number. We have an even number. So what is the midpoint of this data array? It's halfway between 5 and 6. So when you have an even number, you take the two middle and take their average. 5 plus 6 is 11, divided by 2 is 5.5. So in this case, the median is 5.5. What's the mean? We got 50 is the total, right? What's the average? What's the value? What's the sum of them? No, the 50 is the sum. We've got 1, 2, 3, 4, 5, 6, 7, 8 values. So our mean is 50 divided by 8, which is what? 6.25 is our mean. Our mean and our median are not the same. We've got more. We have other measures of central tendency. The next is called the mode. The mode is simply the one that's biggest. It's the value that occurs most often in a data set is called the mode. Okay? And I stand corrected. It's not the one that's biggest. The biggest would be 18, which would be here at the 82 midpoint. What is the mode here? Well, we've got 2 5s and we've got 2 1s. So really in this case, neither one of them occurs most. There's not one data that occurs most. So this one has no mode. But think back to that, that frequency chart where you counted up, where you took the raw data and you counted the tallies. That's what we should really be looking at here. And then you plot your frequency as a tally. Okay? That's actually what these frequencies are, tallies. That means there were 18 patients who had between 80 and 84 was their value. Okay? In that case, this is the mode. All right? Right here. 82 is the mode of this data set. Okay? And we actually did this wrong when we did this. Because what we really would be calculating is a weighted average or a weighted mean. Because we would say, well, we've got 18 of 82. And we're going to get there in a minute. Okay? Of that data set, if we took this back to a raw data set before we did the tallies, then we would find that the mode is 18. And if you'll recall, when we looked at the different kinds of shapes of the frequency graphs, one of them was where you had 2 peaks, like that, and that was called bimodal, 2 modes. So if we were going to treat this as a mode, a question, then it would be bimodal. It would have modes of 5 and 1. Okay? We're not going to go there. The mode is simply the one that has the most tallies in it. The value that occurs most frequently in the raw data. And if it only has 1, then it's called unimodal. If it has 2, then it's bimodal. If it has multiple peaks, then it's called multimodal. Next, we have mid-range. Okay? The mid-range is simply it's not, I won't say close, it's an approximation of the average. It's the average of the highest and lowest value. You take the highest value, the lowest value, divide by 2. And if we were talking about this, it would be 18 minus 1 is 17, which would give us a mid-range of, yeah, what would that be? 8.5. Okay, but that's of this. That's not of the actual raw data. The raw data goes from 99 down to 60. So 99 minus 60 is 39. 39 divided by 2 is 15 plus 4.5, 19.5. Which means the mid-range would be, I didn't hear it, 19.5. Now, what's the average of this? Well, again, we're going to have to talk about a weighted average to calculate that. And I think that might be what's next. Yep, the weighted mean. They use an example in here of average cost. The average cost of a gallon of gasoline for 3 taxis. Well, they don't all buy their gas at the same place, so each one of them is going to pay a different price per gallon. But they also don't all buy the same number of gallons. So you have to talk about how many gallons did they buy at this price, plus how many gallons did this guy buy at this price, plus how many gallons did this guy buy at this price, and then divide all of that by the total number of gallons that they bought. Okay? Look at it this way. Look at it based on unit analysis. We're talking about cost per gallon times gallons plus cost per gallon times gallons plus cost per gallon times gallons. Okay? Those all cancel, so the numerator of this equation is just cost. In other words, how many dollars did this guy spend? Total cost number 1. Total cost number 2. Total cost number 3. Right here. Divided by the total number of gallons they all bought. And you end up with a total cost per total gallons, gives you an average of all 3 taxis. Okay? That's a weighted mean. It's how you calculate things whenever they're not all, they're not all equally balanced. When you have, in this case, we don't have the raw data. So we can't calculate the actual mean of the raw data. But we can do a weighted mean based on the frequency that we have. Okay? We don't know if, we know that 18, we're between 80 and 84. So we're going to say we got 18 at 82. Now, that may have been, some of them were 80, some of them were 81, some of them were 83, some of them were 84, but we're going to say we got 18 at 82. So, we have 18 times 82. And I'm not going to have enough room to do that here. So let me find a place to do it over here somewhere. Let's just start at the top. We have 2 at 62 plus 1 at 67 plus 5 at 72 plus 12 at 77 plus 18 at 82 plus 86 at 87 plus 5 at 92 plus 1 at 97. And we're going to divide that by how many? 2 plus 1 plus 5 plus 12 plus 18 equals 50. Okay? That's how many total measurements were made. We made 18 measurements that came into this class, 12 measurements in that class. We made 50 measurements altogether, divided up between 8 classes. So now, what is 2 times 62? You got your calculator going? That's 124. Okay, can you keep a running tally as we go? And what's 1 times 67? That's going to be 67. 5 times 72. Plus 12 times 77. What's 12 times 77? Plus 18 times 82. Plus 6 times 87. Plus 5 times 92. Plus 1 times 97 is 97. Do we have a total of that? Preaching to the choir. $4,030 divided by 50. Gives us 80.6 is our weighted arithmetic mean of this frequency distribution. And it's probably pretty close to what the average of the raw data, what the mean of the raw data would have been. Okay? So we can talk about this data set as having a mean of 80.6 and a mid-range of what? 99 minus 60 was 39 divided by 2. No, I'm sorry, 99 plus 60 is, divide that by 2. 79.5. And now, what's the mode? 82. What would the median be? Well, we don't know because we don't have the raw data. So we can't calculate the median or the actual mean. But we've got the weighted mean of the raw data and the mid-range of the raw data and the mode of the raw data, and they're not that far apart. That says we've got a mode of 82 mode, a mid-range of 79.5, which is also a boundary, and a mean of 80, and a mean, that's the mode, is the 80.6, so 79.5, 80 the mean would then be right about here. So you see we've got mid-range, mean, and mode. And they're all pretty close to the center of this frequency polygon or histogram. That means that this is a fairly close to normal distribution. If it was skewed right or skewed left, then we would have a mean way over here, a mid-range somewhere way away, and a mode way off over there. If this were a perfectly Gaussian, perfectly normal distribution, then all three of those would be one value, right in the middle. All five of these actually, median, mean, mode, mid-range, weighted mean, they would all be the same. And class is over. We ran out of time 5 minutes ago.